right, here we go. So today we are going to talk about describing angular motion. Right. So honestly, everything here is going to be a review from stuff you went through in honors last year, with the exception of the addition of calculus, which seems like a pretty big thing, right? But I'm going to basically plow through the definitions and the equations that are review, and really try to focus on the aspects that are new. Okay. So here we go. So obviously, you know, we've been talking about linear motion, right? So one of the sort of fundamental pieces of linear motion is talking about linear displacement, right? Which is a measure of how far or how much an object's position changes on a linear number line, right? So this chapter, instead of talking about motion on a linear number line, we're going to be looking at motion around an angular number line, okay? And so instead of calling that linear displacement, we call it angular displacement. The symbol we learned last year was delta theta, where theta is angular position, delta is change in angular position, and so this whole symbol means angular displacement. All right, we're going to use the same kind of coordinate system, the same quote-unquote number line that you would use in math class, which is, you know, this circle at 3 o'clock is an angle of 0. We're going to use radians for reasons which I'll discuss here in just a second. So as you go around, you're going to get, for example, pi over 4, pi over 2, 3 pi over 4. Pi radians, right? Okay. So if, for example, you've got an object on, whatever, merry-go-round or something, and it goes from a position of pi over 4 radians all the way around to pi radians, then your change in angular position would just be 3 pi over 4 radians. Okay. So super quick, just refresh your memory about these things. Now, why radians? So when you talk about angle, obviously you're measuring some portion of a circle, right? And historically, we always use degrees, right? In which case you take your circle and you chop it up into 360 easy equivalent sizes. But there's nothing magic about that number 360. There's no reason why we couldn't, arbitrarily divide our circle up into 4 bits like this. So here's a quarter, here's a quarter of a revolution, 1 quarter, 2 quarters, 3 quarters, 4 quarters, right? So there's nothing magic about 360. You could divide it up into however many bits you want. So what often makes sense is to do this. One of the things we know from math is that the circumference of the circle is the radius times 2 pi. So why don't we break the circle up into, instead of breaking it up into 360 parts or 4 parts, let's break it up into 2 pi parts, okay? So 2 pi is about 6.28, right? And so what ends up happening then is each chunk corresponds to 1 radius, right? So if my circle has a radius of r, then what that means is if I travel a distance of r 6.28 times around my circle, I'll have gone all the way around it, right? So here's r, that's 1, 2, 3, 4, 5, 6.28, right? Okay, and so each of those arcs of length r, so when you travel a distance equal to the radius of the circle around the perimeter of the circle, you've subtended or swept out an angle of 1 radian. Okay, and so it gives us this relationship. The displacement that you travel linearly is equal to your angular displacement times your radius. Okay. So, as a quick, simple example, what am I doing? As a quick example, so suppose you had a circle with, I don't know, let's say our circle has a radius of, say, 5 meters, and let's say we wanted to travel a displacement of 8 meters around it. Okay, well, how many radians would that be? Well, mathematically, it's this. If delta x is delta theta times r, that means delta theta is delta x over r. All right, and the math here is easy. I want to say a quick comment about the units, though. So check it out. It's 8 meters over 5 meters, but that's actually, when you use this r, it's actually a conversion factor. You're literally converting meters to radians. So here it's 5 meters per radian. So when you divide this out, you get 1.6 radians. Okay, which makes sense, right? That's, so here's my circle. It's got a radius of 5. So if I go 5, that's 1 radian. plus a little bit more, 1.6, right? So there's 5 plus 3, 1 radian, 0.6 radians. Okay, so there you go. All right, now, one of the things we learned last year is, so this equation here that I just glossed past, this guy here was the first in a list of what I called jumper equations. Now, again, to be clear, those are names that's a name I came up with. And I call them jumpers because they allow you to convert between linear and angular values, all right? And the way all of the jumper equations work is this. Your linear value is always equal to your angular value times the radius. All right, and so the first one we've just learned is this, delta x is delta theta times r. Incidentally, notice c equals 2 pi times r is a simple example of that, right? Okay, oops. All right, and so as we go through the video here, we will learn a couple more of them. And for no reason, I'm going to go through it now. So here's the other ones. So linear velocity is equal to angular velocity times radius. Linear acceleration is angular acceleration times radius. Okay. So those are the three that we're going to learn here in the video. Again, those are all reviewed, but there you go. All right. So headed down that path. So, you know, obviously when we talk about the motion of an object, we can talk about linear velocity, where we call it v, all right? We'll sometimes call that linear velocity. Sometimes we call it tangential velocity because it is tangent to the circle, the direction is, okay? The angular counterpart of that is angular velocity. We use the symbol Greek letter omega, lowercase letter omega, to represent that, okay? And as I said a minute ago, you've got this jumper equation that connects the two, okay? So like I said, we talked about that a ton last year, all right? Oh, I guess I should talk about units real quick. So remember your angular velocity. Oh, darn it. So regular velocity is measured in meters per second. Angular velocity is measured in radians per second. Now notice, a lot of times I'll give you frequency. Frequency is in rotations per second, right? And you can definitely convert, right? Because you could multiply one rotation is 2 pi radians, and now you've got angular velocity, right? Now there's an equation on your sheet, the AP physics sheet that says this, which to me has always seemed like kind of a dumb equation because angular velocity and frequency really measure the same thing, just in different units, right? So all this is doing is just converting your rotations to radians, okay? They both measure how quickly a thing is spinning, right? If I say that something spins 10 times per second, that's the same as saying that it spins 20 pi radians per second, right? It's literally the same thing, okay? Just different units. All right, so a quick sign-up note about signs. If you move on and take E&M, eventually you'll learn what's called the right-hand rule, which allows us a concrete way of assigning positive and negative values to angular quantities. For the purposes of what we're doing this year, just with mechanics, I've never found a good reason to use the right-hand rule. So we're just going to stick with basically what we did last year, which is this. Anything going, what's that, counterclockwise is positive. Anything going clockwise is negative, okay? Just like you do in math class, okay? Yeah. So, let's see. All right, so we talked about linear velocity and tangential velocity, blah, 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 blah. We've got all this. All right, so in terms of calculus, so we know that velocity is the derivative with respect to time of position, right? It tells you how quickly your position changes with respect to time. So by the same argument, angular velocity tells you how quickly your angular position changes with respect to time. So if you can't read that weird font there, it says angular velocity is the derivative of theta with respect to time. Okay? And once again, you still have that same jumper equation we've been using. Okay? All right, let's see, what else? All right, so linear acceleration. So, well, linear acceleration, I guess I should say average linear acceleration, is change in velocity per unit time. So that's just VF minus VI over T. All right, so the angular counterpart is exactly what you'd think. Your average angular velocity is change in, no, I said that wrong. Average angular acceleration is change in angular velocity per unit time, omega f minus omega I over t. Again, to be clear, that's just giving us an average, but you do have the same jumper equation, okay? So our linear acceleration, A, is always equal to our angular acceleration. Remember, it's the Greek letter alpha. I know a lot of you guys were calling it fish last year, times r, okay? And again, this works whether you're talking about average or instantaneous or initial or final, whatever, it doesn't matter. Okay, those equations always work as long as you know, both sides are the same corresponding type, whether it's average or initial or final or whatever. All right. Here again, just another reminder that anytime you use one of these jumpers, you have to be using radians. I think I've already made that clear. Oh, it's like a whale. Okay, so let's see. Acceleration is how quickly your velocity changes with respect to time. Angular acceleration is how quickly your angular velocity changes with respect to time. So we've got the same exact relationships with our angular quantities that we do with our linear quantities. Okay. All right, so this is it. This is the list of equations we had to deal with last year, right? So these are our kinematics equations. These work for constant acceleration only. All right, so you guys are still mixing that up where you're using these equations when your acceleration is not constant. That is a big no-no. All right, these guys are analogous. They work when you've got constant angular acceleration. Okay, so if you're somebody who's made the mistake of using these guys when it's not constant acceleration, please be extra careful. Same thing over here. If your angular acceleration is changing, you cannot use these equations. All right. So, we did a ton of these types of problems last year. So I think the only thing I want to do is take a second and do an example that actually uses some calculus. Before I do, let me do this real quick. This will help tie things together again real quick. So, position to velocity, oops, to acceleration. So the derivative of position with respect to time, derivative of velocity with respect to time. So that's your derivatives. You can do change in velocity, oops, change in position is a definite integral of velocity with respect to time. Change in velocity is a definite integral of acceleration with respect to time. Okay. And certainly you could do indefinite integrals, but I think I've hopefully made myself clear that I really think these definite integrals are the way to go. All right, and then so in terms of angular, kind of the same idea. Theta, d theta, dt is angular velocity. The omega dt is angular acceleration. Change in theta is the integral from T1 to T2 of omega dt. And change in velocity is the integral from T1 to T2 of alpha dt. Okay, so I think those are pretty much all four of the calculus equations you would need. All right, so let's do an example here, I guess, and then we'll call it good. feeling really self-conscious here. There are people in my room taking a test right now while I'm recording this video. And I'm, instead of talking to them directly about it, I'm passively aggressively talking to you in the video about it. So there you go. They're shaking their heads in a disgusting fashion at me. All right. All right, let's see. So we got this bicycle wheel. The air valve on the bicycle wheel is this angular velocity. And we got to answer some questions about it. So, oh my gosh. There we go. All right, so just in case you can't read it, here's what it says. Angular velocity is 5 times t to the 4th minus 6 times t cubed plus 4t minus 4. All right, so our angular velocity is changing. All right, the problem tells us if the valve is at an angular position of 3 radians at 0 seconds, I'm going to write theta at t equals 0 is 3 radians. And the valve is 0.4 meters from the center of the tire. Then, and we got to find some stuff. All right, so let's do part A. Part A wants the tangential acceleration. All right, well, tangential acceleration, so we're looking for this guy, right? Because remember, tangential acceleration is just fancy speak for linear acceleration, right? So why don't we find the angular acceleration and then use a jumper? Okay, so our angular acceleration is the derivative of our angular velocity. So we're just going to take the derivative of this mess with respect to t. So if you do that, you get what? 20t cubed minus 18t squared plus 4. Okay, so now we can figure out specifically what that is at 2. So I can find alpha at t equals 2 by just plugging 2 in there. And to do that, you end up getting, well, let's see, it's 20 times 2 cubed, I don't know why I'm writing this all out, times 18 times 2 squared plus 4. So if you plug this into your calculator, you get 92 radians per second squared. Oh, cool. So let's see, but we're looking for the tangential acceleration, so I'm going to use a jumper. So A is just alpha r, right? So 92 radians per second squared times our radius, which is 0.4 meters per radian. This, the radians do, in fact, cancel. You get, what, 3 point something other, or 36.8? 36.8 meters per second squared. So there you go. There's your tangential acceleration. All right, find the valve's radial acceleration. What the? We haven't even talked about radial acceleration. What is radial acceleration? All right, so this did come up briefly when we did circular motion. So if you don't remember, you should write this down. Radial, in the same way here. We'll write both of these things down. So tangential is fancy speak for linear, and radial is fancy speak for centripetal. So we're looking for radial acceleration. That's the same as centripetal acceleration. So for part B, radial acceleration, i.e. centripetal acceleration, that's v squared over r. So I guess we could either find our velocity, or our angular velocity, then use a jumper. Let's do this though. Remember, v is just omega r. So this is omega r squared over r. Well, that's just omega squared times r. Aha. That is a new equation. It is on your equation sheets. And I think, weirdly, that for whatever reason the AE board decided that was the only centripetal equation, or centripetal acceleration equation they give you. I think that's it. Oh no, they gave you both. So both of these are on there. All right, but anyway, often this one is handy. Okay. So, what do we want to do? What do we want to do? Let's see. We want to get, holy cow, what just happened? So, so for part B, to find our centripetal acceleration, our radial acceleration, I'm going to do omega squared times r. So I need to find omega at t equals 2. I'm going to square it, and I'm going to multiply by my radius. So omega at t equals 2 is, I'll just plug 2 in. I'm going to spare you writing it out, but if you plug that in, you end up getting 36 radians per second. So our radial acceleration is omega squared times r, so 36 radians per second squared times your radius is 0.4 meters per radian, and it gives you 518.4 meters per second squared. All right. The units here are weird, and a lot of this has to do with how this centripetal acceleration equation is derived, so I wouldn't get too tangled up on it. You know it's acceleration, it's got to be meters per second squared. Okay, sometimes radians behave strangely. They sort of appear and disappear in ways that are often tough to see without going back through the derivation of the equations. All right. All right, and then last example. Find the angular position after 2 seconds. So, all right, find the angular position after 2 seconds. So I guess there's a couple ways of doing this. Again, I really encourage you guys to stick to those definite integrals as much as you can. So we've got our angular velocity. Let's do this. Let's find the change in angular position during the 2 seconds. So change in angular position is the integral from 0 to 2 of our angular velocity with respect to time. So that's the integral from 0 to 2 of that mass, 5t to the 4th minus 6t cubed plus 4t minus 4 dt. So take your integral and you get, I guess I can just do it, what do we got? T to the 5th minus, what? 1.5 t to the 4th. Yeah, we wrote this. Plus 2t squared minus 4t, and then evaluate it at 0 to 2. So 0 is going to give you 0, plug in 2, and you get 32 minus 24 plus 8 minus 8. So you end up just getting 8. So that is our change in theta. So here's why I say you don't have to do the definite integral. So now all I'm going to do is I'm just going to go, okay, well, I know my change in theta was 8. I know my initial theta was 3. Oh, so that means since delta theta is theta f minus theta I, I've got 8 equals theta f minus 3. Add 3. Final angular position is 11 radians. There you go. All right, so nothing mind-blowing there, despite the fact that I just did a whole bunch of calculus. But I guess my point is it's very, very similar to what we did last year and back in chapter, whatever it was, 1 at the beginning of this year, right? All right, how do we do? 23 minutes, I'll take it. Have a good day.